Problem number 4985. In this problem, we are given that the difference of set A minus B equals to intersection A, A intersection B complement. Well, this is given by definition of what the difference between two different sets is. And the problem asks us to find the union of A and B using the only intersection and complements. So how can we do that? How can we express the A union B using only complements and intersection? So one of the possible solutions is to use double complement. What is the involution property here? Involution property says that if we have A union B complement, it is the same as complement of the complement. It's like the same thing, right? So this is called involution. And then we can apply the De Morgan's law for this particular expression inside, which gives us A complement intersection B complement, and then there is another complement. And so that's basically it. This is our result. That's what the problem asks us to do. And here's another problem. Let's try to prove that A intersection B minus C equals A intersection B difference A intersection C. So how can we prove this? Well, there are two main ways to prove that. The first way is object level, and the second way is set-theoretic. If we try to approach that from object level side, from object level perspective, that would be something like for any x belonging to A intersection B difference C, that would be equivalent to saying that x belongs to A and conjunction x belongs to B and x does not belong to C, which is equivalent to x belongs to A, conjunction x belongs to B, conjunction x doesn't belong to C, which is equivalent to saying that x belongs to A and conjunction x does not belong to A, yes, and then x belongs to B. And disjunction, this one always contradiction, this one always zero. But since we have disjunction here, this is equivalent to the original expression, which is A in A, x in A, conjunction x in B, and x is not in C. We did this for a very particular reason, a very specific reason. We can now apply a distributive property here. We can factor out this part, which will give us x in A, conjunction x and B, and applied. What is that? Is it supposed to be conjunction here, right? X is not in A, disjunction, x is not in C, which is equivalent x in A intersection B, conjunction x, conjunction negation of x in A, conjunction x in C, which is equivalent to x in A intersection B, conjunction of x belongs to or does not belong to A intersection B, intersection C, which is equivalent to x in A intersection B, conjunction x belongs to A and intersection C complement, which is equivalent to x in A intersection B minus A intersection C. Well, because that's the general formula of it. Therefore, our A intersection B difference C is the same as A intersection B difference A intersection C. And there is another way to prove that. Another way to prove that is just to, resolve the right side of the equation here, which is A intersection B difference A intersection C. It's like using set-theoretic approach. Well, it is the same as A intersection B intersection A intersection C complement, which is A intersection B intersection A, right? C union C complement, which is the same as A intersection B union A intersection B intersection C complement. And one more thing, here's the complement as well. So that will give us contradiction, which is 0, and this one equals to A. We can use association property, which gives us A intersection B difference C, which is the original expression, the original identity here on the left side. So that's pretty much it. That's all the whole proof behind this problem. But let me just visualize this to make it more explicit. If you want to visualize that, we can basically depict 3 sets here and using Venn diagrams. So let's say this is the first part, A intersection B difference C, and the second part is here. This is going to be the Venn diagram for the second case, which is A intersection B difference A intersection C. There are 2 parts. Now let me highlight them. So let's highlight B and C is the red color. Oh, let me just denote that this is A, this is B, and this is C. A, B, and C is here. So if you want to highlight this set, B minus C, that would be this external ellipse, right? Without C, this is the B minus C. And then let's designate this A minus C as the red color. A minus C, here it is. This is A minus C. Now I'm going to use the blue color. Blue color would be for A here. The A is like the whole A apparently. And now if you want to find their intersection, let me use the green color for intersection. This is the final outcome, final product here. That would be their common part. It's gonna be their common part. This is the green part. And now here at this point we have, let me use the blue color for A and B, A intersection B. Oops, I made a mistake, I guess here. This is not supposed to be, it's supposed to be different circle, different area. This is actually the intersection A and C, which is this exact part. And then A intersection B, which is the blue color. Here it is. This is the A intersection B. And then if you want to find their like difference, this is this blue part minus the red part, which gives us the exact same outcome, which gives us this green part. And this green part is essentially this area. So this is the exact same area. You can even visualize that. So here how it looks like using the Venn's diagrams. So here it is. Here's the whole problem. I hope this video was helpful, and thank you for watching.